Oh, hi, my name's Ken Kelly. I'm the Senior Engineer at the National Renewable Energy Lab.
So, Ken, we've been talking about hybrids and the cost of hybrids.
Right.
They run about $3,000 to $4,000 more than a regular internal combustion engine.
Exactly.
And you're saying about a third of that cost or more is because of the power.
Electronics. And what we're talking about here today is we're talking about cooling of the power electronics and the importance of that. About 1/3 of the cost of a Prius or Camry type hybrid vehicle, it goes into the power electronics. It's a critical component that processes all of the traction power between the battery and the electric motor, converting it from AC to DC bidirectionally, back and forth. And you're processing up to 100 kilowatts of power through those devices. You're generating on the order of 3 to 5 kilowatts of heat inside the devices. And
now, if I think about that, my hair dryer is about 1 kilowatt.
About a kilowatt. You know, a clothes iron is roughly a kilowatt and a half.
So
pulled out, as one example, we pulled out the power switches from a Toyota Camry.
Now, the Prius is over here. This is what the Prius's power electronics look like.
This is a Toyota Prius power module, and this is a 55 kilowatt system. So the Prius module, you can see how much space it takes up under the hood. And then when we go to a Camry module, which is a higher power system, you can see that they've made that module quite a bit smaller. Basically takes up the space of a 12-volt battery pack now.
The old lead-acid battery.
The old lead-acid battery. Processing all that heat in a smaller area. And so the heat comes out onto these surfaces, and usually what we do is we mount these devices on something that's called a heat exchanger. Taking the silicon chips just to understand basically the layout of the devices and where the heat goes. So the heat goes to these back plates here, and then we put grease, a thermal paste is put onto these, and then it's mounted onto this large aluminum structure, which inside of here contains those cooling fins. Now that's one way of cooling the devices, and it's fairly effective. But what we would like to do is lower costs. If we can more aggressively cool the devices, we can use fewer devices. So we can reduce the amount of silicon chips inside the component and drive them harder by using better cooling.
So what have you come up with so far?
One example that we've come up with, it's called jet impingement cooling of the electronic devices. So direct jet impingement, here's another example of some devices made by Semicron, and typically they mount their devices to the backside and have some fins. We've developed a system where instead of requiring the thermal grease, we cut away some material and we have individual jet nozzles where the coolant comes in, and there's one jet nozzle for each one of the electronic switches.
But won't that water or coolant hit that silicon chip and mess it up like a hairdryer would with water?
That's right. So we don't want the liquid to come in contact with these devices. So we've developed a seal to protect the devices from the coolant. In another research area that we've developed, we've got something called dielectric coolant. Dielectric coolant can come in direct contact with the chips and spray directly on them. But our overall goal is to really drive that cost down of the power module from about $1,200 down to about $600. So cut it in half or less is what we want to do overall. And the thermal management is one way to help us reduce costs. There are some other activities with developing improved lower cost materials that'll help us bring costs down even more.
Will this thermal management also be used in the plug-in electric vehicles with lithium-ion batteries?
Yeah, we believe so. I mean, as you move to a plug-in vehicles, you're going to have more batteries on board, and the battery portion of the cost is going to become greater and greater. but the challenge for cost is also going to become greater. So we believe you need to reduce costs throughout the system.
On the thermal management, do you also work with fuel cell?
A lot of what we're doing can be applied to fuel cells. Some of the jet impingement technology, for example, could be used internally inside a fuel cell. But the other key element is that these inverters, these power modules, are required for all electric type vehicles. So a hybrid vehicle includes an inverter, as well as a plug-in, a fuel cell vehicle, an all-electric vehicle. All those include inverters. So it remains a critical piece of the overall system. You also have inverters in stationary applications like wind power and stationary fuel cells as well.
Kim, thank you very much.
Sure.